So I'm going to be talking about avoiding communication, not just for linear algebra, but beyond that. But before I tell you why I want to avoid it, I have to tell you what it is in the first place. So my model, my simple model of algorithms and their costs I'm going to be using is that they do arithmetic and they do communication. And that means moving data, either between levels of a memory hierarchy, so it could go from the registers to the L1, to the L2, to the L3, to the DRAM and so forth, or it can be between different processors over a network. And I'm going to be measuring the cost in two ways, both by time and energy. So here's my simple model that I'm going to be using to evaluate whether my algorithm is optimal or not. I can count how many flops does it do, how many words does it move, and how many messages does it send. So what's a message? A message is a bunch of contiguous words packed together that you send all at once. And that could be a message in MPI, or it could be a chunk of words like a cache line in the other case. So these numbers depend on your algorithm. And then these numbers depend on your hardware. The time per flop, the time per word moved, or 1 over the bandwidth, and the time per message. And those last two terms are called the communication. So those terms are orders of magnitude apart. The cost per flop in time is much, much less than the time to move a word, and that's much, much less than the time to send a message. And in fact, those three hardware quantities are growing apart exponentially. Now, this is somewhat old data from an old NRC report that I was on. It says they're all getting better by these percentages. That's good. But back when Moore's Law was still in its heyday, the time per flop was getting better at 59% a year, and everything else was getting better much, much more slowly. So what this means is, this is old data, but there was another NRC report from 2011. It's been sort of, there's new data, it's still happening. And so what this means is that even if your algorithm is not communication bound today, it may be next year or the year after that. So we want to avoid communication to save time. But that's not the only reason. Here's a plot of how much energy it takes to do various operations on today's platforms and future platforms. So the vertical axis is the energy per operation on a log scale. This is floating point. The next one is to move data into and out of a register, then to move it a little bit on the chip, to move it a little bit farther on the chip, and then finally, moving it off the chip. And so there's two bars here. The blue bar is today's technology, and the red bar is some predicted 11 nanometer technology that's going to come out soon. And so you can see that in today's technology, there's like a 1.5 order of magnitude of energy gap between a floating point operation and moving the data off chip. And everything is getting better, but it's going to be 2.5 orders of magnitude gap in the future technology. So whether your big concern is the battery in your laptop dying, or the $1 million per megawatt per year it costs to run your data center, or how long you can keep your drone in the air, right? There are different funding agencies. We want to avoid communication to save energy. Okay, so our goals, given all that, are as follows. We want to redesign algorithms to avoid communication, to minimize the amount of data moved between all levels of the memory hierarchy and over the network. And what we want to do is prove lower bounds. We want to show that there's going to be guaranteed lower bounds, that no matter how you write an algorithm, you can't do any better than a certain value. So I'm going to start by summarizing what those bounds are. And the first thing you do is you take those bounds and compare them to standard algorithms and libraries like LAPACK and ScalaPack and other ones you've heard about here. And it turns out that current algorithms are often very far from these lower bounds. And so there's very large savings possible. So let me just give you a summary. I won't have time to talk about all these algorithms. So here's some speed ups that we've attained by using these new ones. So 12x faster for matrix multiply. And 2.5D, I'll explain what that means later. So it's sort of surprising that there was a factor of 12 left on the floor, but left on the table by not using some of these ideas, because people have been optimizing matrix multiply for a long time. Tensor contractions, that's like matrix multiply, except it's higher dimensional than matrices, 3 times faster. All pairs shortest path, so that's graph theory, but it resembles linear algebra in a lot of ways. It's a Floyd-Warshall algorithm. Gaussian elimination, and to get this speed up, you can't do partial pivoting anymore. You still have to pivot to get a correct answer, but it's a different pivoting scheme. And so it gives you a different numerical answer, but it can attain a new lower bound. N-body algorithms, direct N-body algorithms, a factor of 11.8. Tall, skinny QR, so least squares problems on a GPU. symmetric eigenvalue problems. Now, Strawson's method, that's, again, multiplying matrices, but that's not an n-cubed algorithm, that's an n to the 2.8 algorithm. So a lot of these ideas extend to faster algorithms like that. And also iterative methods. And so this is for a bottom solver based on a Krylov subspace method called BiCGstab. And so all of these ideas extend to iterative methods as well. And so you don't have to take my word for it that this is a good idea. You can take the word for it of somebody at a higher pay scale, say President Obama. So here's a quote from a budget request for the DOE budget from 2012. And it says, on modern computer architectures, communication takes longer than arithmetic. And so to minimize communication, you have to reformulate all the communication patterns. And it refers to work being done in the Trilinos library. And so when we saw this, we went and asked Mike Carew what it was referring to. And in particular, they were taking some of our algorithms for iterative methods and for tall, skinny QR and incorporating them in Trilinos. And this was a thesis work of various folks at Berkeley. OK, so that's the introduction and motivation. Are there any questions? Here's the outline. I'm going to survey the state of the art of these communication avoiding algorithms. And I'll begin by just reminding you of the most basic possible matrix multiply and how much data it moves, and then what's been known for a very long time as the optimal way to do it. And then we'll see it's actually not quite optimal. They sort of had a hidden assumption. They were missing something. And that's going to be the 2.5D matrix multiply, and that extends to other linear algebra algorithms. Then I'll talk about tall, skinny QR and the singular value decomposition that goes with that, and then just say a little bit about Strawson. Then I will generalize to beyond linear algebra. It turns out a lot of these ideas came up originally in linear algebra, but they apply to basically any algorithm that you can think of that you could express as a bunch of nested loops, accessing arrays with any number of subscripts you like, any number of nested loops. You can still write down these lower bounds and come up with algorithms which hit optimality. And I'll give you some examples, and that's where the n-body algorithm came from. Now, then, in the, let's see, that must be the third hour of my talk, I'll get to Krylov subspace methods. And I'll say, how do we optimize algorithms like GMRes and conjugate gradient and BiCGstab? That's a different set of ideas. So you can reset. And then finally, in the last hour of my talk, I do have some related topics. We're now learning how to deal with non-volatile memory, where reads and writes have different relative costs. So we had to change our theory and our algorithms to deal with that. And also reproducibility, because a lot of people want to get the same answer every time they run their code, even if they're summing all their numbers in a different order. So let me go on now to surveying the state of the art of linear algebra. And so let me start with direct linear algebra. I'm going to present some lower bounds on communication for problems like, originally it was just matrix multiply, but it turns out it works for Gaussian, solving AX equal B, least squares, eigenvalue problems, and SVD, and so forth. They're not going to be attained by the standard algorithms and libraries. And then I'll talk about the new algorithms that do attain these lower bounds. And there's been a process now going on for a while. There's a lot of software engineering to do to incorporate them into libraries. And I'll talk about the large speedups that are possible. So the theory that I describe tells you here's the design space of the best possible algorithm, but it doesn't tell you all the details of all the constants and block sizes. And so auto-tuning is a tool that we use to try to make sure we get the best algorithm. So let the computer do the work of searching for all the best block sizes. And then let me just say, to summarize, ditto for iterative linear algebra. So we have sort of the same approach. So let me begin now with saying what is this lower bound? And so, and this is a lower bound for anything that smells like three nested loops of matrix multiply. And we have a careful mathematical definition of smells like three nested loops, but your intuition's perfectly good for the moment. So let's imagine I have two levels of memory hierarchy, fast memory of cache of size capital M, and then some big DRAM. And all your data fits in DRAM, but it's too big to fit in cache. So how much data has to move back and forth between the cache and the DRAM to solve your problem? And here's the lower bound. It says the number of words moved by any processor connected to that, that owns that cache, is lower bounded by a multiple of however many flops you assign that processor to do, divided by the square root of its cache size, of its fast memory size. So that is the universal lower bound. And in the parallel case, just imagine I have lots of processors. Each one has its own local memory. That's what the fast memory is. Slow memory is the other guy's memory. Fast memory is your memory. And in that case, the flops is just however many you assign each processor to do. So just imagine you give each processor an equal amount of work, right? N cubed over p or something like that. Now, this has been known for a long time for matrix multiply. It was first proven back in 1981 by Hong and Kung. But now we know it holds for just about everything. It holds for all the BLAs, basic linear algebra subroutines, for Gaussian elimination, for QR, for eigenproblems, the SVD, for tensor contractions, which may have more than 3 nested loops, but they still smell like 3 nested loops. It can apply to whole programs, so not just a single invocation of, let's say, matrix multiply. Suppose you're computing a product, a power of a matrix. You have to do many, many matrix multiplies. The theory says that no matter how you interleave or optimize all those matrix multiplies, you can mix them together, the lower bound still applies. It applies not just to dense linear algebra, it applies to sparse linear algebra. So this number of flops doesn't have to be n cubed. It can be whatever it is that you do on your sparse matrix. You may not know until the algorithm is finished, but the lower bound still applies. As I said, it applies to both sequential and parallel algorithms. Flops per processor is whatever that parallel processor has been assigned to do. And it applies to some graph theory too, because you don't have to do multiplies and adds in the inner loop. You can do maxes and pluses, and that's what, for example, this all pairs shortest path algorithm would do. So that is going to be our lower bound on the number of words moved. But we also want, and so that's the bandwidth cost, call it. But we also want a lower bound on the latency cost, how many messages we send. So here's a very simple lower bound on the number of messages. If I know how many words I have to move, just divide by the largest possible message size, right? That tells me, which could be the biggest cache line or whatever it is, and that'll be a lower bound on the number of messages sent. And so what's a simple universal lower bound on the largest possible message? The whole memory. So my lower bound is going to be just a factor of m times smaller than that lower bound. And in the parallel case, that's the best you can do. So I'm pleased to say they won a Best Paper Prize a few years ago. But this is going to be our goal for reorganizing all of linear algebra. So as I said, the first thing we do is you go to look at the standard algorithms in the old versions of LEPAC and ScalaPAC, and they typically did not attain these lower bounds. They did asymptotically more communication than necessary. And so what we and many others have been busy doing is inventing new algorithms that do attain these lower bounds. So what do I mean by new algorithm? That could mean just doing loop transformations, doing the same operations in a different order, and actually that's okay for matrix multiply. But in general, we need actually new numerical algorithms that have new numerical properties and stability that we have to deal with. New ways to encode the answers. We're going to represent the answer differently, and new data structures, and I'll give you some examples of that. Now, we've made the most progress in the dense case, because that's the easiest one to think about. As I said, the lower bounds apply in the sparse case, but there you have to make some assumptions about your sparsity structure, right? If you want to multiply 2 diagonal matrices, there's no magic, right? The obvious algorithm is optimal. So there are some, if you make the right kinds of assumptions, like you have meshes of a certain kind or random matrices, you need some structure, and then you can indeed prove that there are optimal algorithms. So there's lots of work in progress. So let me just review the basic matrix multiply to remind you how much it communicates, and then how to improve it, what people thought was optimal, and then what's optimal now. So here are the 3 nested loops over I, j, and k, and the inner loop is just doing the dot product of the ith row of A, which I've colored in blue, the jth column of B, and I get the ijth entry of C. So let me just take this code and annotate it with how much data it moves. This is just simple sequential code. So I'm just adding some orange lines here to say where does the data move, assuming I have a cache and that I have DRAM. And I'm going to assume the cache is too small to fit the whole matrix, but I can fit, let's say, a few rows. So I'm going to read in this row and keep it in cache, because I'm going to use it over and over again. Then I'll read that entry, and then I'll read that column and do the dot product. So in the inner loop, everything's in cache. But the thing is that since I can't fit this whole matrix B into memory, every time I go through this inner loop, I have to read that column over and over and over again. So that's where all the communication comes from. But I'm going to keep each row of A in fast memory, so it's only read once. That's a lower bound. I'm going to read A once. I'm going to read and write C once. Can't do better than that. But I'm going to read B n times. And so the total number of reads and writes is proportional to n cubed because of that B matrix, and that completely dominates the n cubed flops, right? Because this hardware operation costs much more, and I'm doing equally many of them. So that's naive matrix multiply. What's the well-known way to do better? It's called blocking or tiling. And so I'm going to still have, in some sense, 3 nested loops, except now I'm going to loop over B over blocks. So each of these little blue blocks is now a B by B subblock. So what do? I have 3 nested loops. I read in these 3 B by B blocks. I assume that B is small enough that they all fit in cache. And then the inner loop is doing a B by B matrix multiply of that times that gets added to that. And I'm assuming that I can fit those 3 B by B blocks in memory, so this line of code expands into 3 nested loops again, but there's no more memory traffic. And so the question is, how much does this communicate? And if you can do all of the algebra, and since I'm assuming that these 3 blocks fit into memory, I'm doing a factor of B fewer reads and writes than I did before. And so if I pick B large enough, I'm doing many, many fewer communications than I am doing arithmetic. So this is the well-known way people have been doing it for decades. So let's just ask ourselves, does this attain the lower bound? I had an assumption that I could fit 3 B by B blocks into fast memory at a time. So, and then that I could hit this lower, then I could do n cubed divided by B reads. So I want to make B as large as possible subject to this constraint. And so B is going to be proportional to the square root of M. And so if I plug that in, I get the number of flops, n cubed, divided by the square root of the cache size, and it attains the lower bound. And so this has been known for a long time. But one sort of thing that people have asked themselves for many years is, what if we don't know M, right? How would I write portable code without knowing the cache size of every last machine that I'm on? Or, what if there are multiple levels of memory? I want to, there's L1 of one size, L2 of a different size. And the answer is something called cache oblivious algorithms, which have been around for a long time. And it's simply write it recursively. Take your matrix, divide it into 2 n over 2 by n over 2 matrices, multiply them, and do it and so on recursively. And I will, I have backup slides if you're interested. That actually also hits the lower bound, assuming you have a reasonable cache that keeps recently used data in memory. So you don't have to know M to hit that particular lower bound. So that's the sequential case. What about the parallel case? Again, this is now one slide of review. How do people multiply matrices in parallel? The algorithm is called SUMMA, which is short for Scalable Universal Matrix Multiply Algorithm. So fancy name. And so what I'm going to do is take my n by n matrix and spread it out on a grid of processors. So I have p processors, in this case 16. And so I'm going to lay them out in a 4 by 4 grid, and each process will own a little n over 4 by n over 4 submatrix. And then what does the algorithm do? It's very straightforward. It does basically an outer product version. So at each step, the algorithm will take a block of this red block of a column of A and broadcast it to all the processors in that process row. That's what those arrows mean. So after this one communication, all these processors will get a copy of that submatrix. Similarly, I'm going to take that subblock and broadcast it down to that processor column, so each one of these processors gets a copy. And so what does each processor do? It's going to get a blue copy from a neighbor in its column, a red submatrix from a neighbor in its row, and it multiplies them and it adds them into its local submatrix. And it just sort of loops over all these blocks, and it turns out that this does attain the lower bound. Okay, and I won't do all the counting, but this algorithm has been around for a long time too. So let me just summarize then, what lower bound does that attain? So I'm going to be multiplying n by n matrices on p processors. I'm going to make this assumption, which seems reasonable for the moment, that I'm going to use as little memory as necessary. So I'm going to assume just every processor owns 1/p of all the data, so n squared over p. Then what's the lower bound say? It's the number of words moved is the number of flops, n cubed over p, it's load balanced, divided by the square root of the local memory size, which is this, and there's some cancellation. I get n squared over the square root of p. That's the number of words moved, and that's attained by that algorithm. And the number of messages is a factor of m smaller, and it's the square root of p. And so that's how many messages I have to send. So the first thing we did is we asked ourselves, okay, does scale a pack attain this particular lower bound? Under the assumption I use as little memory as possible. And for the number of words moved, it mostly did, actually, except for the non-symmetric eigenvalue problem. It did asymptotically more. On the other hand, the latency cost, the number of messages, was asymptotically larger for almost every algorithm in the library, except for Cholesky. Cholesky was quite simple. And so the first thing that we did is we invented new algorithms for all of these to attain lower bounds for both the number of words moved and the number of messages for all these basic problems. And so that made us happy. But then we asked, can we do better? And so I just claimed this was optimal, so how can we do better? And the thing is, I had this assumption, which seemed reasonable, which was I was using as little memory as possible. But the lower bound is still true even if you use more memory. And so the question is, if I have a small matrix on a big machine, I have lots and lots of memory. Can I use it to do something useful? It turns out that people had found a special case of this, and in fact reinvented it many times. It's called three-dimensional matrix multiply. So why is that? The algorithm I showed you where I laid out the processors in a square grid, root p by root p, we'll call that two-dimensional matrix multiply. You can also take all the processors and arrange them in a cube root of p by cube root of p by cube root of p. So that's how you arrange the processors. And it turns out it can do a factor of this, and it uses this much more memory. It uses a factor of p to the 1/3 times as much memory, and so it makes m bigger and it communicates less. And so the question is, how do we take advantage of that observation? But we can't always assume we have that much memory. So if I had 1,000 processors, which isn't that big, I could only use this algorithm if I had 10 times as much memory, right? That's not necessarily available. So let's go on to how we generalize to use as much memory, use whatever memory you have available on the machine. And so I'm going to call it 2.5-dimensional matrix multiply, because it kind of interpolates between the 2D case and the 3D case. So I'm going to assume that I have enough memory to make C copies of my data, right? And C depends on your machine. I could make 2 copies or 4 copies or whatever. And so what I'm going to do is take all my processors, P of them, and arrange them in this kind of 2.5-dimensional grid. They're going to be C layers, and each layer will have P over C processors arranged in a square. And so here's a picture of what it looks like. And so, and I'm going to index them by I, J, and K in that particular way. And I'm going to assume that initially my data is only spread out on the top. So this top layer has a copy of the matrix A and the copy of the matrix B. And so an n over 4 by n over 4 submatrix in each processor. And then, so what does the algorithm do? It's in 3 lines. What it does is it takes each copy of the submatrix A, B, and C, and it broadcasts it. So each layer gets a copy. So that's how I'm using the extra memory. Then each layer runs 1/6, in this case 1/2 of the summa algorithm. It computes 1/6 of all the partial sums that matrix multiply needs to compute. And when we're done, all those partial sums are sitting on top of one another. And then the very last step is just to do a reduction. I vertically sum all the partial sums, and the complete answer appears on the top layer. And I won't do all the algebra, but that turns out to hit the lower bound no matter how much memory you have. So the question is how much benefit you can get from this simple optimization. And here's a factor of 12. So just to give you one example. So this was doing a 8,000 by 8,000 matrix multiply on 16,000 nodes or 64,000 cores of an IBM BGP. And you might say that's a tiny matrix to waste on all those cores. And indeed, if you use the standard algorithm, the 2D algorithm, you'd be running at like 4% of the peak machine speed. It isn't worth doing. But if you use 16 copies, that turned out to be the optimal number, and that fits easily. You're going 12 times faster, and you're running at about 25% of peak speed. So that's for a small matrix. For a bigger matrix, 128K by 128K, you also get a speed up, only 2.7, and that's because that's much more floating point bound. So we got rid of most of the communication, but the time that was left was still arithmetic. So let me do a little more of a timing breakdown to see where did I get this factor of 12 and 2.7. So here is the same data, but now I'm showing you how much time was spent in communication, that's red, how much time was spent in idle, sort of waiting for messages to move around, that's blue, and how much time was spent doing real flops, that's green. And so there's the 2D algorithm, and there's the 12 times faster algorithm where I made 16 copies. And so you can see there was a 95% reduction in communication, so the red went down to there, but even the flops went faster. So how could the flops go faster? Because I'm doing the same flops. And the answer is the local BLAs ran faster because I was calling them on larger submatrices, right? And if you call the local BLAs in a larger submatrix, it runs faster. And so that was better too. Now, in the bigger case, you can see the flop time, the green stuff didn't change very much. It was compute, 1/3 compute bound. But I still got rid of most of the communication. And so if this is where all your energy went to communication, I still may have saved you a large fraction of your energy use, but the flops are still there. So let me now talk about how this enables us to do something called perfect strong scaling in both time and energy. So what's scaling mean? Strong scaling, I'm going to have a fixed problem size, I'm going to increase the number of processors, and I want to solve the same problem faster. And so the idea is that every time you add a processor, you're not just getting more flops, you're getting more memory, right? Because every processor comes with memory, and you paid for it, you might as well use it. And so what I want to do is ask, if I take advantage of that extra memory every time I add a processor, what happens to the runtime and the energy usage? So I'm going to just do a little scaling experiment. And I'll start with a minimal number of processors. So I have just barely enough to fit my 3 n by n matrices on p processors, each one of which has memory of size m. And I'm going to increase p by a factor of c and use all that extra factor of memory as well. So here's going to be a very simple model for timing. I'm going to count the time per flop, gamma t, the time per word moved, that's the inverse bandwidth, beta t, and the time per message. And then I can write down a simple, somewhat messy formula that says the time to solve the problem on C times P processors is this. Now, I don't want you to read that. I just want to understand how it scales. And it scales perfectly. The time to solve the problem on C times P processors is exactly C times faster than on P. The flop time went down by a factor of C. The bandwidth time went down by a factor of C. And the latency went down by a factor of C. So that's perfect strong scaling. So all the costs go down. So that's the best we can hope for in time. So what about energy? I'm going to also make an energy model. And so I'm going to count, and so now the subscript E is means I'm counting joules. So this is the joules per flop, the joules per word moved, the joules per message. But that's not the only place that you burn energy in a computer. The memory burns a lot of energy too, so let me add a term for that. So I'll count the joules per word of memory used per second, just to keep that all alive. And then, of course, there's the fans and the leakage and the air conditioning and all of that. So let me just add one more term, which is the joules per second for everything else. And so again, I can write down a big, long, messy formula. And all I want you to do is notice how it scales. And it scales perfectly. I can solve the same problem C times faster using no more energy than I did before. Everything scales perfectly. So how could that be? That seems a little funny. So I have C times as many processors. They're all burning power at the same rate, and they all take 1 cth as long. So the C's cancel, and it's the same total amount of energy. And so this same modeling applies to n-body and Strassen and all sorts of other algorithms that you can get this potential perfect strong scaling. And you can actually extend it and say, what constraints am I imposing on my network in order to attain this? And you can actually prove lower bounds on the network needed in order to attain these lower bounds. So for example, for matrix multiply and 3 nested loops, you basically just need a 3-dimensional torus where you can talk in all 3 directions at the same time, which is a pretty common network on modern machines to hit this. So let me just show you some more speedups. And this is for Gaussian elimination, both with and without pivoting. And again, so this is without pivoting in the 2-dimensional algorithm using 1 copy of the data. This is, again, no pivoting where I'm using all the memory that's available, the 2.5-dimensional one. And again, most of the communication went away, and it went a factor of 2 times faster. Pivoting is expensive because there's more communication, but there's a new way of doing it, which we call tournament pivoting. I won't have time to do it. I can answer questions later. And it is stable, but it's not partial pivoting. And again, that can get rid of a large fraction of the communication. Now, I should say that when we first tried to do Gaussian elimination, we tried to do it in a way where both the latency went down with the extra memory and the bandwidth went down. And we tried, and we failed. We could make the bandwidth costs go down, but we couldn't make the latency cost go down. So what do you do when you fail to invent an algorithm that you want? You prove a new lower bound that says it's impossible. So here's a new lower bound that says that perfect strong scaling is impossible for algorithms like Gaussian elimination and QR because they have because they're more complicated. They have a more complicated dependency structure. You have to work your way down from the top corner to the bottom corner. It's not like matrix multiply where you can do anything in any order. So if you have an algorithm like LU, here's the new lower bound. It says no matter how you organize it with more memory or whatever, the product of the latency and the bandwidth is lower bounded by n squared. So if I make the bandwidth smaller by using more memory, the latency has to go up because their product is lower bounded. And so there's an interesting trade-off there in how you design your algorithms. OK, so that's enough about that topic. Let me go on to QR, which turns out to be a rather different looking algorithm. So let me suppose I have a tall, skinny matrix on 4 processors, and each processor is assigned 1/4 of the rows. So each one of these W sub i's is mapped to processor I, and I want to do its QR decomposition. So here's what the algorithm is going to do. I'm going to start by doing no communication at all and just doing a local QR decomposition. So each processor just computes factors its local submatrix into Q times R. And so I haven't communicated yet. So what have I done implicitly? Implicitly, I have factored my original matrix into the product of this block diagonal orthogonal matrix and a stack of 4 triangles. That's not the QR decomposition. I want 1 triangle. But I'm making progress. I now have 4 triangles. So then what I'm going to do is I have to communicate. So I'm going to take each pair of triangles, put them together onto one processor, and do its QR decomposition of this 2 little triangles on top of one another. And again, I notice that what I've done is I've taken these 4 triangles and I've factored them into this block diagonal orthogonal matrix times half as many triangles as I had before. One more step, I take the last 2 triangles, do QR, and now I see that I have a 1R, and that is the R of the QR decomposition. And the orthogonal matrices here are the Q, but they're represented in this implicit way. So I factored W into the product of that orthogonal matrix times that orthogonal matrix times that orthogonal matrix times R. And that is the QR decomposition represented as a list of little orthogonal matrices, so that's going to be my new data structure. And anything that you could do with the old representation of Q, you can do with this one. So let me sort of summarize what I just did with this one little picture. Basically, I just called MapReduce, or MPI reduce, where my reduction operation is QR. I take one submatrix there, one submatrix there, do QR, and pass it up the tree. So that is all I had to do to make that work. So that's the optimal parallel algorithm. So what about the optimal sequential algorithm? It turns out it's exactly the same. I'm just going to use a different shaped tree. So here's the optimal algorithm that does QR, and it only touches the data once. So suppose my matrix is in DRAM, but I can only fit 1/4 of it into cache at once. I'll bring in the first quarter of the matrix, do QR. Bring in the next quarter of the matrix, stack that triangle on top of that, do QR. Bring in the next quarter. And so I only have to read the matrix from slow memory to fast memory once, and I get a QR decomposition. So what if I have a dual core processor? I might have a slightly different shaped reduction tree. But what if I have a real computer? It's multi-core and multi-socket and multi-rack and out of all of that stuff. What I'm going to do is just choose a reduction tree dynamically. Whatever hardware resources I have available, I can choose the right shape of a reduction tree and come up with the QR decomposition optimally. And I'll have a different representation of Q, but that's OK. I can use it. My software has to adapt to it. So let me just give you some performance improvements here by doing this. Different trees and different processors. So on an Intel Cloverton, on a very, very tall, skinny matrix, there was an 8x speed up compared to doing it the other way. This was a Pentium 3 cluster, so with an old interconnect now, that was a 6.7x speed up. 4x speed up on a Blue Gene. This was doing it on an on an NVIDIA GPU called Tesla. That was a 13x speed up. This was an interesting experiment. There were 4 French cities. Each one had some of the data, and they were connected over the internet. And it went 4 times faster to do it over 4 cities versus doing it on 1 city. So there was perfect speed up. So you can imagine there's a lot of latency going over the internet between different cities, and so this could hide the whole thing. And we also have this implemented originally in Hadoop, and now it's also available in Spark, which is a widely used big data algorithm. It's only like twice as slow as doing a single MapReduce. So that's about the fastest thing you can do on a platform like that. Now that's all parallel speedups. The best sequential speedup we got was actually infinite. So how do you get an infinite speedup? In this case, the student was trying to do a big matrix so big that it didn't fit in DRAM, and it had to use virtual memory. And he just got tired of waiting for the standard algorithm to run. He sort of gave up. Now then, the new algorithm was only about twice as slow as though he had infinite DRAM. It almost completely hid the cost of accessing the disk. So I'll just call that an infinite speedup. And I should say that if you want to do the singular value decomposition of a tall, skinny matrix, this is the first step. And so all these speedups apply to the SVD just as well. And I'm pleased to say this won another Best Paper Prize recently. Okay. So there's lots of ongoing work in this. And I didn't have time to talk about it all, but let me just point out there's symmetric indefinite factorization, Austin's method, variations like that, so LDL transpose. There's pivoting for the QR decomposition. There's many other pivoting schemes. Eigenvalue problems look completely different. Sparse matrices, HSS matrices were mentioned. I don't actually have any slides on those, so sorry, Lori. All pairs shortest path. Doing it where there's one copy of the data or multiple copies of the data. So getting this on all sorts of different platforms. I should say the lower bounds apply to heterogeneous platforms because they're processor by processor lower bounds. So you can assign different amounts of work to every processor and still figure out what the lower bound is. And we're trying to get this into software, but let me just say there's lots of open work to do and into applications. Okay. So let me now finish with this sort of direct stuff by just a little hint as to what happens when we do not n-cubed algorithms, but asymptotically faster algorithms like Strawson. So let me just, to compare, I'm going to restate the lower bound I just told you. I'm just going to rewrite it slightly so that the fact that it's a cubic algorithm appears that it's n cubed, and there's a 3 right there. But this is the same bound I had before. It's n cubed over the number of processors divided by the square root of m. So why did I write it this way? It's so it make it easy to compare to Strawson. All I have to do is change 3 to log base 2 of 7. And that's how many flops I do, and that's how much communication I have to do. That's the new lower bound. So this makes the typesetting easy, but the proof is actually much harder. And I won't go into all the details. So that's what it is for Strawson's algorithm. But Strawson was invented a long time ago, and people have been inventing new, faster algorithms ever since. Strawson is practical. The other ones are theoretically interesting. And it applies to most of those too. So if anybody ever invents a new n to the omega matrix multiply, then the lower bound for communication just change that exponent to an omega, and that will work. And so the proof uses all sorts of different ideas from graph expansion, and there are some assumptions that you're doing the sort of a recursive thing with the same recursion at every level. And we also had an assumption about the graph, but fortunately one of Jacob Scott, one of the PhD students of my co-author Olga Holtz, just wrote a very long thesis and removed that assumption. So this is now much, much more general than it was before. And we also showed that this works even if you have more memory. So you can keep going faster, same trick as before, but there's a limit. And this limit applies not just to Strawson, but applies to all of matrix multiply. There's a hard limit. For matrix multiply, it would be n squared over p to the 2/3 memory. Past that, you can't go any faster. If you keep adding memory, it keeps scaling that nice way that I told you about until you hit that particular memory size, and then it stops. And there's this, that's a hard communication lower bound. And I'm pleased to say this won another Best Paper Prize. So now the question is this lower bound attainable? So let me show you some performance data. And so this is a strong scaling plot on Franklin, an old Cray XT4, for a really big matrix, 94K by 94K. The horizontal axis is the number of processors in a log scale. The vertical axis is the effective gigaflops. So this 2n cubed divided by the time. So this is so I can compare fairly an n-cubed algorithm with a Strawson-like algorithm. So up is good. Up is sort of inversely proportional to time. And this horizontal line, this green line here, is the peak speed if you run an n-cubed algorithm. So if communication were free, you could go that fast. So this green line, that's scale-opaque, the classical n-cubed algorithm, no copying of the data. This green line is the n-cubed algorithm where I use all the memory available, and it's getting reasonably close to the peak speed of the machine. These blue lines are previous attempts to parallelize Strawson, and the red line is our new algorithm. And you can see that this is nearly horizontal, and it's faster than the peak speed of the machine because Strawson is doing fewer than n-cubed operations. And so this says that since this line is horizontal, this says doubling the number of processors means I go twice as fast. So I get nearly perfect strong scaling out pretty far. And so this stuff is practical. And I think this is the world's fastest matrix multiply, at least at the time we did this. And this was invited to appear in the CACM. Okay. So that's enough about linear algebra. What I want to do is say how this generalizes to basically anything that smells like nested loops, which is an awful lot of code. So I'm going to do that by just illustrating what I mean by smells like nested loops. But let me just do that for matrix multiply first. So there's the naive code, just to remind you. I have 3 nested loops over I, j, and k. And there I'm doing a matrix multiply inside. And again, just a reminder, what is the optimal code? We know that we have to break it up into blocks. So I'm going to have 3 outer loops, which are going to loop over B by B submatrices. And then I'll have 3 inner loops, which do a B by B matrix multiply. And the theorem said that if I pick the block size right, and it happens to be m to the 1/2, then I can hit the lower bound. And the lower bound is n cubed, the number of flops, divided by m to the 1/2. So the question is, where does this 1/2 come from? What is so special about 1/2, and how do I generalize that to arbitrary code? So let me apply the new theorem without proving it, just to this new code to show you what I need to know. So there's the nested loops, and all I need to know about this code I can record in this array. And this array says there's 1 row for every array. This matrix records all the information I need about the communication. So there's 1 row for every array in the code, ABC, ABC, and there's 1 column for every loop index, IJK, and so IJK. And all the matrix this says is that which arrays have which subscripts. So matrix A is subscripted by I and K, so I get a 1 there, a 1 there, and a 0 there, because it doesn't have J as a subscript. So that's a very simple just description of what the code does. So the theorem goes on to say, I'm going to solve a linear program with this little 3 by 3 submatrix. What's the linear program? It says, please maximize the sum of these 3 numbers subject to the constraint that this matrix times x is less than or equal to 1. And the answer to this very trivial linear program is 1/2, 1/2, 1/2. And the value of the linear program the sum is 3 halves. And I'm going to give that a name, S sub HBL. HBL are the initials of 3 famous mathematicians. I will tell you who they are. You can guess in the meantime in a couple of slides. So that's what the theorem says. You do that simple math. And it goes on to say that no matter how I organize this code, the number of words moved is going to be the number of flops divided by m to the solution of the linear program minus 1. So that's where that 1/2 comes from. And how do I optimize it? I have to block it. What are the optimal tile sizes? It's m to the exponent, the solution of the linear program. So m to the 1/2, m to the 1/2, m to the 1/2. So that's what the theory says for linear algebra. It just tells us what we knew. Well, let me apply it to something else. Let me apply it to the direct n-body algorithm. This is even simpler. I just have 2 nested loops, and I take over I and j, and I take pairs of particles, pi and pj. I compute some arbitrary function, and I update the force on particle I. So now when I record the same information, it's the same matrix. There's 1 row for every array, pi, pj, and f. Those have different subscripts, so they get different rows. There's 2 columns for index I and index j, and I have 1s and 0s. And I solve exactly the same linear program that I did before. It's even simpler. And the theorem says that no matter how I reorganize this, I have to do at least n squared to the power divided by m to the first power. So this is even better than matrix multiply. Matrix multiply was m to the 1/2. Now I can communicate even less, and it tells me what the right block sizes are. And I'll show you the speed-ups in a couple of slides. But just one more example, just for shock and awe, to show you how general this theory is. So I wrote down a random 3 lines of code. And there's 6 nested loops, there's 6 arrays, they have random subscripts. I just kind of made it up. It's not real. But everything I need to know about this mess, I can embed in this 6 by 6 matrix of 0s and 1s. And it's the same as before, 1 row per array, 1 column per loop index. I solve the same linear program as before. It's now 6 by 6, no big deal. And out pops this magic number, which is 15/7. And so the theorem says that no matter how I reorganize this mess, I have to do at least the number of loop iterations divided by m to the 8/7 words moved. And it tells me how to do the optimal tiling. And so this is something you can imagine putting into compilers. And we're talking to the compiler community about this. So here is, as I said, matrix multiply. All I need to know about it is that I have 3 nested loops. And they're iterating over some subset of triples of integers. And I'm accessing locations indexed by ij, ik, and kj. That's all I need to know. And in the general case, I can have as many loop iterations as I want. I can have as many arrays as I want. And I can have any subscripts. And they can be messy things like I2 plus 3 times I4, whatever I want, as long as there's some linear functions. And I can have pointers, so I can have indirection. And I can have as many lines of code as I want. And it turns out that all I need to know about that, again, I just sort of say I'm iterating over some subset of k tuples of integers, and I just keep a list of all of these subscripts. So for example, C has this one subscript, and so I'm just going to record that by saying there's a mapping from all the loop indices to the subscript of C, and there's another mapping from all the loop indices to the subscript of A. And just to give you a taste of what the math is like, these are called group homomorphisms. So that's where the math is going to come from. So don't worry about it if you haven't heard it before. But that is sort of you can think of them as linear operators. OK, so my goal is to have communication lower bounds and optimal algorithms for any program that looks like this, where I can sort of describe it by, in this simple way. And so given a subset of loop iterations, how much data do I need? So I'm going to have this list of homomorphisms, and I need to somehow write down a lower bound. And it turns out that this is where the HBL came from. The famous mathematicians are Holder, Braskamp, and Leap. And they wrote down a linear program which said that if I can solve this linear program, then I can, where these are just integers, so these are like dimensions of vector spaces. They have to be satisfied. And if I can satisfy that, then I can use this recent result of Terry Tao, who's a brilliant mathematician at UCLA, to write down a theorem in functional analysis, which turns into, and I was assured that they had not thought about the application to computer science when they were doing this. Here's the theorem. If I can solve this linear program, then the number of words moved, no matter how I reorganize the algorithm, is lower bounded by however many loop iterations they are. It could be dense or sparse, whatever you like, divided by m to this magic exponent, which comes from solving the linear program. And so what we are in the process of doing is trying to, make this algorithmic, because the mathematicians say there exists a linear program that's, and then we can use it. But to actually compute this linear program, when we first tried to do it, it turned out it was undecidable as to whether it was possible to write down or not. But then we reformulated it and we made it decidable. And here are the speedups that we got from doing this. So this is for the n-body algorithm. And so if I this theorem generalizes the fact that we can use more memory too. So if I just have one copy of all the data, then I'm running, most of my time is spent in this is the n-body problem on 32,000 particles on 8,000 cores. So each particle, each core is only getting 4 particles. So it seems like you're going to be communication bound. And indeed, if I just have one copy of the data, then I'm spending almost all my time in this green area, which is the communication, and very little doing computation. But by the time I get up to 64 copies, then the communication is gone, and I get a factor of 12 speed up. So that's what's possible there. So this works not just for 2-particle interactions, it works for arbitrary many-particle interactions, because people in physics are also interested in 3-particle and 4-particle. It all generalizes. And let me just give you some applications, including one you probably haven't heard of before. So obviously, people are doing this for gravity and turbulence and molecular dynamics. I have colleagues at Berkeley who do electron beam lithography to help make devices that can make chips faster. But we also, I should say, Kathy had a graduate student who spent a summer working at Disney. It's used to simulate hair. And so if you've ever seen the movie Brave with Princess Merida, her hair is simulated by doing n-body interactions. So each hair has a whole bunch of particles that repel all the other ones, and whenever she moves her head around and the hair shakes, it's done by doing these kinds of n-body interactions. And so so this has been used in Disney movies ever since. And the only bad news is that if you only spend 3 months working at Disney, you don't get screen credit. So the student, Michael Driscoll, his name does not appear, unfortunately, but he still gets the credit for this. So ongoing work is to, as I say, get this to be automated enough that can go into compilers. We have yet to find a case where we cannot attain the lower bound, and we have some progress in trying to prove it's always attainable, but you'll have to wait till next year to hear whether we've succeeded in doing that. And as I said, we can use extra memory as needed. Okay, so now in my last hour, let me quickly talk about Krylov subspace methods. So in this case, I'm going to be solving either ax equals b or ax equals lambda x. And how do these algorithms work? As many of you know, I'm going to do a bunch of sparse matrix vector multiplies, repeatedly do a matrix vector multiply, build up a sequence of vectors, and then choose some linear combination of those vectors that gives me the best solution to my problem. And this is a high-level description of a great many algorithms like conjugate gradient, GMRes, Lanczos, and so forth. And so my goal is to minimize communication in these. And the expensive stuff is going to be, we're doing all of these matrix vector multiplies over and over again and all those dot products. So to keep your intuition going here, so this is a completely different intuition than in the first part of the talk. Let me assume the matrix is well partitioned, so imagine a finite element mesh. So what's the serial implementation? Every time I go through the inner loop, I have to do a matrix vector multiply. I have to read my huge sparse matrix from DRAM to cache. And so the conventional algorithm, the cost of communication is going to grow proportional to k, if I take k steps of the algorithm. The new version is going to take k steps of the algorithm and move the data once. And 1 is a lower bound, obviously. So I'm going to somehow reorganize all of these different algorithms to take k steps, even though I've only read the data out of slow memory once. That's the sequential case. In the parallel case, imagine I'm spreading the work out over p processors. What's the conventional algorithm going to do? At each step, it's going to do a matrix vector multiply, and it has to do a dot product. A dot product costs log p messages to do the reduction. So the cost is going to grow like k times log p. That's going to be the latency cost. The new algorithm is going to do 1 reduction, or maybe 2 reductions, and to still take k steps of the algorithm. And so that's going to be another large factor of speed up. And so this is going to give us both a bunch of modeled and measured speed up. I'll show you data. The price is twofold. We're going to do some redundant computation, but flops are cheap, so I don't mind doing that. But what are the challenges? If your matrix is not well partitioned, then it becomes interesting. Incorporating preconditioning is a challenge. There's some ongoing work. And it turns out if you do this in sort of the obvious way, it's not numerically stable. You have to be clever to keep it numerically stable to do this transformation. This gives you exactly the same answer in exact arithmetic, but in floating point, it's much trickier. So let me just give you an example of how it works. So what I want to do is replace my matrix vector multiply inner loop with what I'm going to call the matrix powers kernel. So I'm going to compute not just one matrix vector multiply at a time, I'm going to compute a whole bunch of them. And I want to do that by touching the data once. And I'm going to illustrate it on a very, very simple matrix where I can draw every detail, a tridiagonal matrix. So imagine A is just going to be 32 by 32, and it's tridiagonal, and so I'm given all these 32 entries of x. I want to compute all those 32 entries of ax, a squared, and a cubed. So what do I need to do? So since my matrix is tridiagonal, I know that every entry of ax depends on 3 entries of x, and I've drawn the dependencies there. And of course, this picture repeats itself everywhere. So that entry of a times x depends on those 3 entries of x. And to make the drawing a little bit easier, let me just fill in the triangle. So everything at the tip of the triangle depends on everything at the base. And so, for example, that entry of a cubed x, I need to know those 3 entries of a squared. And if I keep those dependencies growing, I eventually need to know all those entries of x in order to compute that entry of a cubed. Of course, I want to compute not just one entry, but I want to compute many entries. So to compute all of those entries, I need everything at the base of the trapezoid. So that's my dependencies. So now, how do I minimize communication? Suppose I can fit only a quarter of my data into fast memory in the sequential case. So I'll read in a quarter of the entries of x, a quarter of the rows of A, and I have enough information to compute everything in that blue trapezoid with one communication. Then I can write out the answers, and I will save those 2 diagonals and read in the next quarter of X. Then I can have everything to compute everything in that red parallelogram with one communication. Then the same trick, I go on, I can compute everything in there and everything in there. So I've touched everything once, and I've communicated, but I've taken 3 steps of the algorithm. That's the sequential case. What about the parallel case? Suppose I have 4 processors, and I want each processor to compute a quarter of all of these entries. So ideally, it would just compute everything there. What does this depend on? It depends on some data from the neighbors. That's the shape of the trapezoid. So what would the standard algorithm do? It would communicate at every level, sending one number from processor 1 to processor 2, so processor 2 would just compute that. So instead, what I'm going to do is package up all of these three numbers into one message and send them all at once to processor 2. And the same thing for these three. Then processor 2 has all the data it needs to compute everything in that red trapezoid. And so there's going to be redundant computation. These little triangles at the end are going to be computed twice, but that's OK, because it's going to minimize communication. So the total dependencies would look like this. Everything in these overlapping triangles gets computed twice, but these are small compared to the whole thing. So that's the picture for a tridiagonal. What about a general sparse matrix? So it's very much the same idea. So now I've represented my sparse matrix as a graph. Each node is a row or a column. Each edge is a non-zero. And I've partitioned the matrix here so that this processor, the yellow processor, owns these rows. And then it also needs some other data. So what data does the yellow processor need to compute A times X? Well, it needs the neighbors. And the neighbors are just follow the edges out, 1. And those are the entries of X that are needed for this guy to compute A times X. Go one more level out, one more breadth first search. It needs the green ones to do A squared times X. And follow out a third edge, and it needs the blue ones. So that's the equivalent of those trapezoids on the previous page. But now it's sort of a graph traversal. And so in order to figure out how to optimize this, I needed to find these partitions. And so instead of just simply tiling the tridiagonal, I have to do some graph partitioning. And then I need to decide what order to do these in. And there's no obvious left to right order anymore. It turns into the traveling salesman problem. So that is going to give me these numbers, which is a new basis for my Krylov subspace. But I still have to go back and say, well, what do I do with it? How do I actually solve AX equal B? So here's the standard GMRes. I take k steps. I do a sparse matrix vector multiply. I run modified Gram-Schmidt to make that vector orthogonal all the previous ones. And then I solve a little k by k least squares problem. So that's standard GMRes. Here's the new one. I'm going to use that kernel that I just told you about to compute this new basis of the same space that I did before. I still need orthogonal vectors. That's just going to be a QR decomposition, doing tall, skinny QR on this new basis. And I still solve the same little least squares problem. And so if you do all the counting, in the sequential case, I've hit the lower bound. I've only read the data from slow memory to fast memory once, and I've taken k steps of the algorithm. And in the parallel case, the number of messages has decreased by a factor of k. And everything I've said here is completely true in exact arithmetic, but there's a terrible bug in floating point. Because what is this kernel doing? It's taking powers of the matrix. This is called the power method, or PageRank, if you like. And so all of these vectors are getting more and more nearly parallel to the dominant eigenvector, so I'm going to lose precision. But let me do a numerical experiment and just see what happens. And so here is the convergence of GMRes, classical GMRes, on a big matrix. And let me just run the algorithm I showed you. Here's the convergence plot, or the lack of convergence plot. And that's because those vectors are so nearly parallel to one another that I just lose it all. But there's no reason that I have to use these particular polynomials, a squared, a cubed. I don't need to use monomials. I can use any polynomials I like, as long as they increase in degree. So if I'm clever and pick the right polynomials, it converges perfectly. So I just have to pick the right polynomials so that those vectors maintain their numerical independence. And so everything works fine. And so here's some more speed-up plots. This is just on an 8-core Intel Cloverton. So now there is communication to avoid both on-chip, off-chip, and in between the different cores. And you can see that the speed-ups, I can't go into all the details, were both by making tall, skinny QR run faster and because of the matrix powers kernel. So I should say that when the students first tried to optimize this, one student was optimizing the sparse linear algebra. One was doing the dense linear algebra. They put it together, and it slowed down dramatically. It was terrible. And they realized that was because they were both, the two optimized linear algebra routines were competing for the cache. And so then they realized they had to co-tune the kernels to realize they were sharing those resources, and then we got those speedups. So it's possible, but it means you can't have separate libraries anymore. So that was GMRes. I'm just going to show you a little candy. BiCGStab works too. It's a little bit more complicated to make all the algebra work, but it is possible to reorganize that. And there's more tricks to make it numerically stable. And the speedups now, and this is for the bottom solver for geometric multigrid, and then some real applications of 2.5x speedup for low Mach number combustion and for gas dynamics. So all of this extends to machine learning. So if you guys want to hear about how to make machine learning algorithms run faster using the same ideas for coordinate descent, we've just started working on that, and many of the same ideas apply. And so to summarize, there's new lower bounds, optimal algorithms, big speed-ups, and there's still lots of work to do, especially with preconditioners. I won't have time to say about how all this extends to non-volatile memory, but when writes are much more expensive than reads, you have to get new lower bounds on writes, which are smaller, and optimize that separately, and we can do that. And so let me just say that I teach a parallel course in this, and you can get free supercomputer accounts from the National Science Foundation if you want to spend a semester working on all this stuff. And there's a 155-page survey article. And this is joint work with a large number of people, and I won't read all their names. I will point out Kathy Yellick, with whom I collaborate very closely, both on avoiding communication and raising two children, which sounds like a contradiction, but you just have to be careful about what kind of communication you avoid. Don't avoid the wrong kind. And so, to summarize, it's time to redesign all linear algebra codes, n-body algorithms, software, and compilers. And what it all has in common is don't communicate. Happy to take questions, or we can just go to the break and do questions.
N by n matrix, and you divide into tiles. How do you define what is the size of the tile that you should take?
So is this the dense case or the sparse case?
Dense case.
In the dense case, the theory says that it's going to be the fast memory size to some exponent, like square root of m by square root of m. But that is what the theory tells you. In practice, you have to choose the constants, right? Because it might be half that or 1/3 of that. And the one way to do it is, of course, tuning by hand, which you start with. But our long-term goal, and we're building tools for that, is to do auto-tuning, so that you will, automate, the code will search over all the right tile sizes. But now we know roughly how big it is, so it will do it'll make searching much easier, and it'll pick the right size for you.
So for each platform, you will be choosing a different size depending on the platform?
Yes, it's all hardware dependent, because M, is the size of your L1 cache, L2 cache, L3 cache, and so that will be dependent on the platform. And so three ways of handling that, as I said, are auto-tuning. The other one is cache oblivious algorithms, where you just write recursive code, and it turns out there's some beautiful theory that says it adjusts automatically. And the other way is we collaborate closely with folks like Intel, and they take our algorithms, and they have a team of ninja programmers in Novosibirsk, and they do all the hard work. So, yeah, so thanks to them.